Okay, so what are large language models and how do they work? If you've been paying attention to the world of computers at all since late 2022, you've heard of ChatGPT. This is an automated chatbot that can respond to any prompt in somewhat human-like ways, taking advantage of information that's out there on the web. It can even write computer code and also hold conversations in any human language that is well represented online. Beyond ChatGPT, there's Gemini from Google, Claude from Anthropic, the open source system Llama from Meta, and various others, as well as systems built on top of these as backends. These systems are not perfect, and it's not hard to push them in ways that reveal their failures, but they are remarkably good at what it is that they do, and they somehow provide an easier way to interact with all the information on the web than usual search engines do. They're useful in ways that no human interaction can duplicate, even though they can't do most of the things that humans can. In some ways, they're good enough at what they do to encourage people to rely on them, even for things that they're bad at. But hopefully, once you understand the basics of how they work, you can get a sense of how to reduce these problems. Now, one thing to keep in mind, I'll often talk about these systems as though they know things or think things or learn things or remember or try or imagine or hallucinate or whatever. This is all just convenient shorthand. They're built on systems that are somehow patterned off of the neurons in our brain, but there are important differences. Now, we tend to call these systems as a whole large language models, or LLMs for short. But technically, it might be better to refer to the system as a whole as a conversational AI or a virtual assistant. The LLM is only a component of the whole system, and there's also a wrapper that enables the chat interface and makes them hopefully more helpful, harmless, and honest. In this lecture, I'm going to discuss both of these parts, the LLM and the wrapper. There are, of course, many other sources that you can consult on the internet to learn more details about any of this. Lots of YouTube videos, textbooks, blog posts, even asking the large language models themselves. Okay, so what is the core LLM itself? As the name suggests, it's a model of language, not a model of a language like English or Arabic or Chinese, but rather language as a whole. And importantly, it's not a model of language as an abstract system, the way that 20th century linguistics wanted to study. It's the concrete messiness of language as people actually use it, not just what is grammatically correct, but what people actually say. 20th century linguists thought it was important to separate our knowledge of the world from our knowledge of language in order to study each one separately, because they're interested in language as a separate part of things that are going on in the world. So for instance, according to linguistics, the sentences "she ate the sandwich" and "she ate the airplane," the important thing about them for linguistics is that they're both grammatically correct sentences. Now we should ignore for linguistics that one of them describes a more common state of affairs than the other. That's just a fact about what people eat. We're not studying diet here, we're studying language. And according to the language, both of these sentences are fine. Linguists also care more about what words did someone mean to say rather than what actually came out of their mouth with all the ums and uhs and likes and false starts and so on. Now, as we're going to see, a large language model is going to represent all of this. It'll include the knowledge of the world and the common human desires, and as well as the knowledge of language, and it'll also include the kinds of slips and errors that people tend to make. The LLM isn't going to bother trying to sort any of this out. It'll say, the sentence, "she ate the sandwich," that's a good sentence. People say that all the time. The sentence, "she ate the airplane," that's going to be somewhat questionable. It might occasionally occur. It might be the sort of thing that happens, but it's not going to be common. So the question is, what does it mean to be a model of language in this sense? And if there's one thing that you're going to learn about what a large language model is, you should learn this. An LLM is a way to guess the probability of what word comes next. And there's three important words here. The probability of what word comes next. So why probability? So in astronomy, people made all sorts of models of the solar system since antiquity that try to say what will definitely happen. The moon will definitely be in this phase tomorrow. There will definitely be an eclipse after some number of months, so on. But language is much more complex than that. 20th century linguists thought that, in fact, language was too complex for us to say anything about probability. They thought all we'd be able to say is just which structures are grammatical, and anything about probability would have to build in people's desires and knowledge of the world and other stuff that's outside of language. But it turns out LLMs do fine trying to deal with all of that. But as we're going to see, this is going to include everyone's biases as well as their knowledge. Now, why words? Technically, a large language model doesn't know what a word is. And words aren't even a useful construct in some languages. In many languages like Turkish or many of the indigenous languages of Northern North America, there's just a single word for the sentence that has lots of little prefixes and suffixes that convey all the connections between the things that we would represent as different words in English. The large language model, instead, what it's going to do is it just gets a huge amount of text and it tries to break it down into the units that it can do the best job of predicting. And it'll call these tokens. Humans actually work with units that are smaller than words too. So, for instance, in English, consider the sentence, plastic decomposes slowly. We usually say that's 3 words, but linguists will say this is made up of 6 morphemes, which each have their own meaning. Plastic, decompose, z, slow, and li. In some languages, each one of those would be represented by a separate word. In other languages, we'd combine it all into a big word. It turns out that what LLMs do is they take this text, divide it into whatever units they use that they can best predict. These are what they call the tokens. These aren't going to be quite the same as words or morphemes, but it's close enough. They're usually bigger than individual letters, except when they're dealing with very rare words and phrases. And it's usually not whole sentences or phrases, but something more like morphemes. Now, why predict just the one that comes next? This might seem sort of trivial, but it's actually fairly deep. When you speak or when you read across the page, spoken and written language do unfold just token by token in order, either through time or on the page. If you could always just make a guess about which token comes next, then you could use that word as part of your context that helps you predict the next one, and the next one, and the next one, and so on. And this seems to be something like how words flow off our tongue when we're speaking. But that's not exactly how grammar works. And so linguists noticed if we look at questions in English, the question, where is he going, is related to the sentence, he is going home. But the words come in a different order. And linguists said, somehow there must be some deep structure in which both of these sentences are represented, and then they get transformed before they come out of your mouth. And somehow the initial representation is not going to correspond to the order they come in. Occasionally we say things like, he's going where? But usually we reorder things. And now the interesting thing is, large language models don't worry about the deep structure. They just go word by word. And yet they manage to get these patterns just right. And so the fact that it works somehow tells us something really deep and powerful. Okay, so as a recap, a large language model, LLM, is just a way to guess the probability of what token comes next. And it's useful to keep this in mind when interacting with it to help you understand the ways in which it is and isn't like a human. Obviously, the fact that we are able to produce fluent speech, sometimes holding a complex conversation with lots of interruptions, means that we must have some sort of automatic system for just producing the words one by one, rather than planning the whole paragraph, figuring out what each sentence is, then organizing the words, and then finally starting to talk. But at least sometimes we do plan, like especially when we're writing papers or books or things like that. And the large language model doesn't do that. There's no planning involved. It just goes word by word by word. There's a lot of reasons that linguists thought that something like this shouldn't be able to work at all. So the fact that it works is impressive, but understanding the ways in which how it works is different from us is helpful for understanding what kinds of errors it'll tend to make. Okay, so a large language model is a very simple thing. How is it possible to have a conversation with it? Now, with the early large language models, things like BERT or GPT-2 that existed between 2019 and 2022, what you would do is you would put in the first few words or sentences of a document, and it'll just continue the document, predicting what's the next word after this. If you put in something like, what is the capital of France? It might continue 1 point. What is the capital of Germany? 1 point. What is the capital of Italy? 1 point. And the reason it'll do that is because the question, what is the capital of France, doesn't occur much in the training data except as parts of a test. And so when it occurs as part of a test, the thing that comes next is another question and another question. One of the big breakthroughs that produced ChatGPT and then all the other modern conversational AIs is that there are special kinds of documents in which questions like this don't get followed in this way. So there are some documents that say something like, the following is the transcript of a conversation between a client and an assistant. Client, what is the capital of France? Assistant. And if you put this into one of the old LLMs, it would then follow up with something that would naturally come out of the mouth of the assistant. Maybe something like, the capital of France is Paris. Anything else I can help you with? And now the way that a conversational AI works is by putting in this text before sending your prompt to the LLM. And they call this the system prompt. And what you put in is what they call the user prompt. And the idea is they only show you the user prompt, but the LLM at the back end gets the user prompt plus the system prompt. And this tiny tweak, it's a very small thing, but it made ChatGPT so much easier to use than the earlier LLMs. And so suddenly hundreds of millions of people started paying attention to this. And one thing you can look up is the paid versions of almost all of these LLMs allow you to modify the system prompt in various ways. And so you can try that out. Now, there's one other layer that they add on top of the LLM itself. The large language model is representing the probabilities of all types of text that it's been trained on, but some of that text isn't good. Some of it includes students who are answering questions incorrectly or assistants who aren't being helpful. Some of it is people giving harmful advice on how to build bombs. Some of it is insults or scams or deception. And because all of this stuff is in the training data, and the large language model is just trying to duplicate the kinds of things that are in the training data, it'll have some chance of duplicating any of these. And so what they're going to do is they're going to do an extra layer of training on top of this, where they try to make it be helpful, harmless, and honest. And to do this, what they do is they have the LLM interact with humans. In the case of OpenAI, this means that they use English speakers in Kenya and India who are cheaper to hire than people in the United States. And what they do is they have those people have a bunch of conversations with the LLM, have them rate how helpful, harmless, and honest each of the answers is. And then they tell the LLM to tweak its weights so that it does more of that and less of the other stuff. And they call this process reinforcement learning from human feedback, RLHF. Since the training data for the LLM already has both the helpful and unhelpful things, and the harmful and harmless ones, and the honest and dishonest ones, it apparently doesn't take a lot of RLHF in order to train it to do a pretty good job on this. The big data is needed for the base LLM, where it gets the predictions about what words come next, and then the RLHF can be a small amount that you actually involve humans in. So now let's come back to the LLM itself. I'm not going to go into all the details in a brief lecture like this about how it works, but I do want to mention a few important features. Early approaches to probabilistic word prediction used a very simple model that we call a Markov process. Markov processes are used for all kinds of other things in science and statistics, but here in the context of language, the way we're going to think about it is that it has a specific amount of memory. It's something that maybe just remembers 3 words at a time, perhaps. And when predicting what word comes next, it's just going to look at those 3 most recent words, see how many times those 3 words appeared together in the training data, and then look at what word came next and count what frequency each of those words has. So let's see an example of how this might work. So imagine we start with the cat's with. So now Uh, it just says, guess a next word. Maybe one possible word is the word black, and then cats with black. Maybe the next word is fur, then with black fur. Maybe the next word is R, black fur R. Maybe the next word is cute, fur R cute. Maybe the next token is a period. So at this point, we've got a grammatically complete sentence. Now, this method, it'll sometimes work to generate good sentences like this, but it runs into big problems. First, you sometimes need more than 3 words of memory to be able to grammatically complete a sentence correctly. So if we jump back to this stage in the training sentence, the only words in the memory are with black fur, and it's going to look at all the places in the training data where those 3 words occurred together. Maybe it occurred both in the cats with black fur and in the cat with black fur. And now the question is, which word could come next? It could be is in the second case, and it could be are in the first case. And both of those might occur in the training data, and so it'll have some chance of giving either of those. But because it doesn't have the memory of the word cat or cats, it's going to sometimes get it wrong. Now, if you only have 3 words of memory, you can't stay grammatical. You might do a little bit better by having a longer memory in this context, but it's unclear exactly how many words of memory you need to get it right. Now, there's a second problem. Even with just 3 words, you sometimes get a set of 3 words that don't have any data. So just looking at the newspaper today, I found these 2 headlines on the front page. And both of them include a sequence of 3 words that has never occurred in that sequence on the internet before. I Googled the phrase Disneyland unions agree, and the only thing that came up was this article. Similarly, the phrase insane viral Olympic, the only thing that came up was this article. If you had trained on text that occurred before, and then you saw one of these sets of 3 words, it would never have occurred in the training data, and it would not be able to continue. And in this case, making the memory longer makes the problem worse. So this is one more reason why people were convinced you couldn't calculate the probabilities of which words came next, because you have these contradictory demands on the information being used. If you have too few words, you can't ensure that it's grammatical. If you have too many, you too often run into sequences that have never occurred before. But there was a major breakthrough in 2017 that fixed this issue. And this is what they call the transformer and what they call attention. And what they did to do this is they took a longer memory, hundreds of words, maybe even thousands, not just 3. But instead of paying attention to every single word and looking for that entire sequence in the training data, they only paid attention to certain aspects of these words. Sometimes all that matters is I had a singular noun 5 words back. Sometimes what matters is there was a verb relating to food 2 words back. Sometimes what matters is you had rhyming words at the 5th, 10th, and 15th positions. And so the 2 things that they needed to do is figure out a way of representing all of the many hundreds or thousands of aspects of a word that could be relevant in some context or other, and a way of figuring out which aspects of each of those words to pay attention to on the basis of the words that came before in a given context. And I won't say anything about the details of how they did that. It involved neural nets in some complicated way. But here's like a sample of how it might work. So we've got these different words, will, marry, cross, dill. Each one of them, I'm just going to represent a whole bunch of different features that these words have, some of them up to 1 and down to 0. So all of these words are fairly high in the noun dimension. Some of them may be a bit less because they might be sometimes nouns, sometimes other things. Will and cross are sometimes verbs, so they're pretty high in the verb dimension, while dill and marry are much lower. Some of them have some futureness to them or some femaleness to them. Note that there's going to be thousands of these different aspects of a word. And then you have to figure out how do you pay attention to which parts of which words do you pay attention to in a context. And what's going to happen is that the LLM has something like this. It's got a partial sentence, and it has to figure out what do I need to look at in order to see the next word there? And here it sees the word she. It sees that she has femaleness in it, so it looks back for a female word, Mary. It sees that Mary is next to the word drink, and so it's going to look for something related to drink. Whereas these attention heads, if they see the word he there, it'll look back and find the word John. It'll see that John is making the drink. And so it might guess maybe in this case, you should say something like the host or the bartender. Whereas if it was she, it was looking for thirsty or something like that. And so by only looking at some aspects of these words, there can be lots and lots of matches in the training data. We don't need to find these exact words, just other words that have some similar aspects to them. Obviously, this is much simpler than the full details of what's going on. These are just toy examples. The real details are much more complicated, and they're based on vast amounts of training data. The training for some of these may include almost everything that's on the internet. And because this is all done by a neural network, no human exactly understands how these things are represented. It just somehow is done by hundreds of millions of numbers in this neural net. You could ask the LLM how this representation works, but it's not going to be able to give you any better answer than a human neuroscientist would ask if you asked her, which neurons is it exactly that are enabling you to think about the brain? So just to wrap up, we know that the large language model is just predicting what word comes next, one token at a time, using probabilities that match its training data and the reinforcement learning from human feedback that was put on top. We know that it isn't explicitly planning anything. Its later words depend on the earlier words that it says, so you can often get better results by asking it to explain itself step by step before giving the answer, rather than just jumping in with the answer. It can start using the early words to plan, and then once it can see that plan, it can use that plan to go forwards better. All it's trying to do is duplicate the kinds of word sequences that it saw in its training data with some modification by the RLHF. The human feedback was supposed to point it to helpful, harmless, and honest, but we can't know for sure if those are the patterns that it saw in the data. Now, linguists thought that it was a problem to try to duplicate the patterns in word use because they wanted to understand how language works separate from what the world is like. But if you're interacting with the LLM to find out about the world, then it's an advantage that it merged these two things, the world knowledge and the language knowledge. In order to predict the text of the reply of a helpful, harmless, and honest assistant, it's probably got to have somewhere in its multidimensional representations of word meanings and somewhere in its matrices for deciding what aspects of words to pay attention to, some representation of what some parts of the world are like. We sometimes say that an LLM is hallucinating when it sounds like something that, when it says something that sounds like the sort of thing a real person would say but isn't true. In particular, these large language models sometimes make up fake court cases or fake papers or fake citations. But when it does so, it makes them up in ways that sound like real things that might be relevant in the situation. And interestingly, humans do this sort of thing all the time too, when we misremember the past in plausible ways. So think, what's the most famous line in the movie Apollo 13? Is it Houston, we have a problem? That line doesn't exist in the movie. What's the most famous line in the movie Casablanca? Is it play it again, Sam? No, that line doesn't appear in the movie either. Both of those are just plausible sounding combinations of words that blend a couple different things that got said in those movies. And enough humans misremembered the movie as containing those lines that now those lines have entered into our cultural context. When people do it, we often call this confabulation. When someone tries to recall something that they half remember, or they try to explain why they did something, they'll usually include both a mixture of the actual facts and things that they're sort of making up as they recall it that sound plausible at the same time. And they don't realize which parts are which. And kids do this especially often. Kids will ask adults questions about why is the sky blue, and then push why on that, and then why on that. But the interesting thing is turn the tables on them. Ask a kid why they're doing something, or why the sky's blue, or why are there lions at the zoo? Kids will often give really interesting answers to that question that they're just making up. Now, they don't realize that there's a difference between making things up and actually knowing the truth because they don't know that very much of the truth. And this is often what's going on with large language models. All they know is that people produce words that look like these sorts of patterns, and they have some idea of what makes it sound right. And so they make things that sound like that. And they may or may not have figured out some of what's really going on in the world in order to better tune some of these patterns. And I think that's a good place to end it because, after all, aren't we all in that same sort of situation some of the time?